All right, so we're going to use this combining power series theorem to try to eventually combine power series. So they give you some setup here. Suppose that two power series are of this form. We have a Cn and then x to the n and the sum of a dn to the x to the n. And they converge to the functions f and g respectively. Respectively means in the same order. So the first one's going to go to f. The second one is going to go to g. And it's going to be on some common interval I. Our first one here, this is going to be sum and difference, where we simply are adding or subtracting the different power series or the different values together. And we're going to get the same thing, f plus or minus g. So if we're adding, we're going to get a plus. If we're subtracting, we're going to get a minus on that I. Not too terrible. You've done other things that are going to be similar to that. This is a product here. And where we have a product, specifically, we're going to multiply our bxm here by our cxn. So we just get a product of the two where we get the new bit, bx to the m, times what our function of f was, that f. Because our c, recall, goes to f up here. This last one is a composition of functions. Where we have an f of g sort of situation. Remember, c of n was our f. And we're evaluating this new bx to the m as part of it. So if we have something where we have to do composition of functions, this is how that's going to work. But with number 63, I'm going to do looks like an addition one. There's a subtraction one as well. I'm going to leave that to you, as the problems should be very similar to each other, but instead of adding, we're going to subtract. So let's see if we can use these. In fact, we're going to use both number 1 and number 2 on this because we're also multiplying by this 1/2. All right, so this is going to equal 1/2 times the quantity. Well, let's look at our f. F is x to the n over n factorial. So let's just evaluate maybe the first 4 or 5 terms here. So it's going to be, when n is 0, we have, well, x to the 0, not 0 something. X to the 0 over 0 factorial. Remember, 0 factorial equals 1. Then we add that to x to the first power over 1 factorial, and so forth. And so on, until eventually we get to the next set, the g's. So we're adding all of the f's are first, and then we get to the g function and we start adding those. And remember, I mean, we're adding, so we can do these in any order. The commutative property works. All right, so when x is 0, we're going to have -1 to the 0, which is just 1. So then we get, again, x to the 0 over 0 factorial. But what happens when we put in a 1 for n? Well, that's -1 to the 1, which is now a negative. And we get this x to the first power over 1 factorial. And then we add again when we get an even value. And subtract again when we get an odd value. And so forth. So what's happening here? Well, when we have the first ones here, there's 2 of them. 2x is 0 over 0. So that's just the number 2. But I'll leave it as, so it's 1/2. We've got 2 times this x to 0 over 0 factorial. But then we can cancel the odd number ones. We've got a positive and minus for the same thing for the thirds, and so forth. So what's happening here is we're going to double all of our even number values of n. and remove all the odd ones. And we can simply, cancel the 2 with all of these other 2's because there will be a 2 in front of each of them. So ultimately what we're going to have here is going to equal x to the 0 over 0 factorial plus x squared over 2 factorial, x fourth over 4 factorial, and so forth. And what does that equal? Well, that's going to equal the sum, n equals 0 to infinity, of x to now the 2n all over the quantity 2n factorial. And again, the negative one will be a very similar process here. Alrighty, so let's see if we can do number 67 here. We've got to go back to partial fractions. So this is going to be of this form. This is going to equal, we can't really break up this x squared plus 4. So it's going to be some sort of ax plus b over x squared plus 4. We'll have a linear over a quadratic there. Then we're going to, x squared minus 1, we can break into x minus 1 and x plus 1. So let's do c over x minus 1, and then we'll use d over x plus 1. Okay, so now I'm using the arrow because my first line is going to infer this next one. If I multiply through by the denominator there that I've just highlighted, we're going to be left with a 5 on this side of the equation. I put the equals to sign there, and then I start, canceling out. Cancel out the x squared plus 4. I'm left with ax plus b times the quantity x squared minus 1. And then I'm only left with, looks like x plus 1 times c, so c times the quantity x plus 1. And, oh, no, we also have the x squared plus 4. Because we're only losing that, we're left with everything else. And I guess we'll have the d with the x minus 1 times the x squared plus 4. So this is what we have when we're trying to solve for everything else. So let's figure out what we want our x to be here. Let's let x equal 1. And I'm using 1 because it's going to cancel out the x squared minus 1. And it's also going to cancel out the x minus 1. So all we'll be left with will be c. So we still have the 5 over here. So again, I plug in a 1 for x squared minus 1, it goes away, and x minus 1, it goes away. So I'm left with c times, what do we have here? 2 times 5. So that equals 10c. And what does this mean? We have 5 equaling 10c, which means c is going to equal 1/2. So not so bad as far as that goes, right? Well, we can do a similar one here. Let's let x equals 1. So we do x equaling 1. Again, that x squared minus 1 is going to go away. And the only thing, excuse me, x equals -1 is what I want. So our first one, x squared minus 1 is going to go away because -1 squared is 1. So it kills that whole first ax plus b. It is also going to kill our c, so we're left with the d. So we've got 5 equaling d times -2 times, well, that's going to be squared, so that's going to be a 5 again, which equals -10d, which means that we have d equaling -1/2. All right. So let's take a, so we've got the c and the d. Let's take a look at the rest. We've got ax plus b. Well, the a has to be 0. Why is that? Well, A equals 0 because there is no x in our numerator. And I'm specifically referring to the numerator of the 5. It's just a 5. So that's helpful. All right, so what else do we know? We also should know this. We get negative b plus 4c minus 4d will equal 5. And this is from distributing all parts. And what do I mean by that? Well, I'm looking at specifically the constants. All right, so what happens when I'm distributing the ax plus b times the quantity x squared minus 1? Well, I'm left with a negative 1b. We'd multiply b using FOIL. B times negative 1 gives us negative b. C will be multiplied by the 1 times the 4. Everything else will have an x in it. And D will be multiplied by the negative 1 and 4. Everything else will have an x in it. So we have this. So we have a couple pieces of information. Now we can start maybe plugging in some stuff. So this should mean that we have the negative b plus 4, and we know c to be 1/2 minus 4, and d is negative 1/2 will equal 5. So that gives us negative b, and then we have 2 and 2 here. We can take all these out, we can solve, and that means b is going to equal negative 1, because I'll have negative b equaling 1, so b equals negative 1. And our c equals 0. So we're going to write down our function. Okay. Okay, so we have 5 over x squared plus 4 times quantity x squared minus 1 will equal negative 1 over x squared plus 4 plus, well, 1/2, so 1 over 2 times the quantity x minus 1, and then minus 1 over 2 times the quantity x plus 1. And we can just pull it, we can leave the 1/2s out, we can do whatever we want as far as that goes. So what does this give us here? All right, so if we're going to turn these into something that looks like a Taylor series, because ultimately that's what they wanted, right? A power series, excuse me. So we need to get it of the form 1 over 1 minus x, something like that, right? So how are we going to do that with these? Well, we can pull out a 1/4 for our first one, or negative 1/4. And we're going to be multiplying that by 1 over 1 minus a negative x over 2 quantity squared. Well, I plugged the 1/2 into this one. I probably shouldn't have. I should just left it out, it looks like. Looks like we're going to take out a 1/2 or negative 1/2. And that'll be 1 over 1 minus x. And similarly, this will be 1 over 1 minus a negative x. So now we can change these into the series that we know. So this will be negative 1/4. And this summation will be our negative x squared over 2. Now we can look at that and break out the negative 1 if we want. And all of this will go to the n. Well, let's see where we can go from there. This next one is, there's our sum, and this is just negative x And our last one will be just x to the n. All right, so we want to ultimately combine this into one power series, so we've got a little bit of work to do. So let's see what we can do. So negative 1/4 sum. We can combine these other two, however. We can combine these guys here. How can we combine them? Well, we already kind of know what they're going to be. We just did a problem up here where we took 1/2 of f plus g and figured out what we had. So we can take out the 1/2 straight up, and we're going to get this x to the 2n x to the 2n for that. So let's go back. So we can pull out, say, a negative wrong guy here. So we can subtract here. We already know what happens to the half, so that's going to be the sum n equals 0 of x to the 2n. And so we've got an x to, we can change this here. And this will be x to the 2n. And we're looking at a negative 1 to the n. And then we've got a 2 to the n. So we can pull some of that out. And ultimately, we're going to get this. So we've got a 2 to the n on the bottom, but we've got this fourth here. So we can add 2 to that. So we've got this negative 1/2 n to the 2 because I'm bringing the 1/4 in, because that's another 2 to the second. And what do we have over here? We've got, we can pull out an x to the 2n, so we'll add 1 and then multiply by x to the 2n. Looks a little, excuse me, this should be equals, I'm sorry. Looks a little funky, but that's sort of the process for it. I should keep my notation here. So there you have it, a little complex problem, but how we would kind of combine things using power series.